Okay, so now at this point, you guys should be pretty good at drawing Lewis structures. And Lewis structures and the types of bonds, the polar covalent, ionic, and the nonpolar covalent, that is kind of the basis for what we're going to be doing from now on. So you have to be really good at everything we're going to be doing from now on kind of builds on that. And so we're going to be talking about something called Vsepr. It stands for valence shell electron pair repulsion theory, but basically it's an idea of what the molecules look like in 3 dimensions. Because when we draw them on the computer, or we draw them on the board, or we draw them on paper, it's 2 dimensions. And that's not really the way things line up. The idea is the areas of the electron density, so the areas of electrons, the lone pairs and the bonded pairs, around the central atom are going to push themselves as far away from each other as possible because they're all made out of electrons, and electrons are negative. And so they repel each other a little bit. So the idea is the central atom, the electron density areas around it, will move the atoms or the electron densities around it as far away as possible. That's what valence shell electron pair repulsion means. So we're going to try and generate 3D models of molecules. We'll bring in the 3D television and we'll show you guys what it looks like in 3D so you can kind of visualize it, because even we can't draw it very well. So the big idea, put a little star next to this, is that the electron pairs around the central atom are going to push each other as far away as possible in 3D space. We are going to attempt to draw that. So carbon dioxide looks like this if you draw the Lewis structure. Around that carbon atom, they have 2 areas of electron density right there. They're double bonds, but they are 2 areas of electron density. And they're going to push each other as far away from each other as they possibly can get. So the fact that we draw them as a straight line is cool. We wouldn't draw them like this. Okay, because they're going to push each other as far away as possible to end up looking like they're in a straight line. So that's what it does. So double bond, lone pair. And again, it's only around the center atom that we're concerned about with these guys. And their shape that they call that, oddly enough, is called linear. So there's carbon, oxygen, and oxygen. Get as far away from each other as possible. CH2O, if you draw it, looks like this. And, you know, depending on how you line it up, that's probably what you draw it as. And again, around that center atom of carbon, we have 3 areas of electron density. And they're going to line up as far away as possible from each other. And so what it looks like is this, where the bond angles, the difference between them is 120 degrees instead of 90 degrees. And so this is a geometry thing. And the name for this one is called trigonal planar. Methane, if you draw it with a Lewis structure, CH4, looks like that. Now you might think, oh yep, that's as far away as they can get it from each other, is 90 degrees. And you would be correct in 2 dimensions. Okay? But what happens is in the real world, because it's not 2-dimensional, they line up at about 109.5 degrees apart. Because in 3D, they can get farther away from each other than they can in 2 dimensions. And this is what it looks like. There's your carbon, hydrogen, 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 and hydrogen. So this one's kind of sticking out, and that one's kind of sticking behind. And then these 2 are kind of in the same plane. So it looks kind of like a jack, if you've ever played jacks before. It looks exactly like that. And it's called tetrahedral. So what happens if you have dots? Because none of the ones I've given you before, what if you have lone pairs on the center atom? Well, the idea is, because they are electrons, they also take up space, and they also push the other electron pairs around them. But you can't see them because they're not attached to anything. But they take up space, and so they get a different geometry based on the fact that they take up space, but they are not visible. And so they get special names. So if you had CH4, which looks like this, or NH3, which looks like this, both of them have 4 electron regions. 1, 2, 3, 4. 1, 2, 3, 4. So essentially, let me erase what I have on the slide because I think it's going to pull this up. That's CH4. Remember I said one's sticking out, one's kind of sticking behind, and those guys are kind of in the same plane. The term for it is electron geometry is tetrahedral because based on the way the electrons are arranged, they line up in this 109.5 degrees. And the molecular geometry is what it looks like is also called tetrahedral because everything is attached to another atom and we can see all of them. When you're doing NH3, you still have those 4 electron regions, one sticking forward, one sticking behind, and then one in the plane. But up here you have lone pairs. So its electron geometry is still referred to as tetrahedral because it has 4 electron regions around it. So the electron geometry is the same as this guy because they both have 1, 2, 3, 4. But you can't see this guy. He's not there. And so what you see is you see kind of this shape like this that isn't flat, still has about 109.5 degrees, but they call it a trigonal pyramid because it's kind of a pyramid shape and it's got a triangle for a base. If you look at water, this is water. It also has 4 electron regions around it. 1, 2, 3, 4. So its electron geometry is just like the methane and the NH3. It is tetrahedral. However, you can't see these guys. They're there, they're taking up space. This is still exactly, or approximately, not exactly, approximately 109.5. But you can't see those other ends, and so they give it a different name. Its electron geometry is still tetrahedral because it had 4 electron regions. But the name they use for it, for its molecular geometry, is called bent. And then the last one, CH2O, remember this is this one, and SO2, electron geometry, 1, 2, 3 electron regions. Electron geometry is trigonoplanar, and all of them are attached to an atom, so its molecular geometry is the same. SO2 has the same kind of thing, 1, 2, 3 electron regions. So its electron geometry is still trigonoplanar, just like this guy. But because you can't see this, what you see is bent. And the bond angle here is about 120 degrees, just like the bond angle here is about 120 degrees. Okay, linear geometry, 2 electron regions, 2 electron regions. And so its molecular geometry is the same. And if you have something that is composed of only 2 atoms, so like you had HCl, it's linear. There's no other way for it to go anywhere else. So quick summary. These are your electron regions, and ACA stands for around central atom. So this is 4 electron regions around the central atom. Lone pairs plus bonded pairs. Okay? The electron geometry is tetrahedral because they all have 4 around them. But if you have lone pairs around the central atom, one of them is called trigonopyramidal. 2 of them is called bent. If you have 3 electron regions, they're referred to as trigonoplanar. If you have 1 electron region around the central atom, it's called bent. And then 2 electron regions is linear. And then if there is no central atom, it's linear. So this is something you guys are going to kind of need to know. I'm not going to give it to you on a cheat sheet or anything like that. I'm going to show you how to draw 3D molecular structures because I guess it's kind of important when we start doing this to kind of visualize it, but I won't expect you to do it on a quiz or a test. So if it's linear, if it's trigonoplanar, or if it's bent, you can draw it in 2 dimensions and it's exactly the same in 3 dimensions. Where you run into problems is anything with tetrahedral and trigonopyramidal. And so you'll need to make some changes. So methane, if you remember, looked like that. That's the Lewis structure. But if you remember the little thing that looked like a jack, what it does is it has one of the H's sticking forward, and we do a little triangle for its bond, and one of them sticking back, and we do dots for it. So that's supposed to represent, these guys are in the same plane as the carbon. This one is sticking out of the wall, and this one's sticking behind the wall. That's the attempt to draw it in 3 dimensions. It's tricky, it takes some time.